Okay, so the second speaker in this session will be Linfeng from Hong Kong University of Science and Technology. Linfeng is currently a PhD student working in the Reconfigurable Computing Systems Lab of Hong Kong University of Science and Technology with the Hong Kong PhD Fellowship. He received his MPhil degree in ECE at Hong Kong University of Science and Technology and BEng in CS at Zhiyao. His research focuses on optimization problems in the middle and back end of high-level synthesis and physical design automation, including floor planning, placement, routing, etc. Over to you, Linfeng.
Thank you for the kind introduction. Okay. Hi, everyone. Welcome to my presentation. I'm Linfeng from Hong Kong University of Science and Technology, supervised by Professor Zhang. Here, I'm introducing one of our recently open source framework called FADO. Well, this work solves a co-optimization problem for high-level synthesis designs. On the one hand, we try to search towards the Pareto optimal HLS directive configurations to minimize the design's latency under resource constraint. But on the other hand, we search for good floor plan to maximize the achievable frequency. It is, okay, let me try to do the highlight. Okay, it is resource utilization that connects these two tasks. Smaller latency really means you have a higher parallelism and more resources needed. However, as the utilization increases, it will be difficult for the physical optimization steps to reach a high frequency. So FADO is the first work to consider the co-search of the directive and floor plan, which is vital for maximizing the performance on multi-die FPGAs. Let's first take a look at the challenges in this co-optimization. Well, first, the design space is very large. There are 26 directives in VITIS HLS 2020.2 version, and each of them has a set of parameters. They can be applied at different levels of the HLS source code, like loops, functions, arrays, etc. So a very large space. Well, second, the directive design space is non-monotonic, which means that in this example, you can see that we compare the trend of resources as the pipeline initiation interval changes. As II increases, well, resource decreases for this CNN design because its computation instances are shared among multiple cycles, so resource sharing. By contrast, because there are lots of loop carrier dependencies in the LU design, extra logic is used to buffer the result between clock cycles. So the resource utilization first goes up, and then it also decreases because of some similar resource sharing mechanism. So this is non-monotonic relationship in the problem. Well, third, the previous work of HLS design space exploration has no physical layout knowledge, which means that it only minimizes latency under an overall resource constraint with a single die scenario consideration. However, the multi-die introduces separate constraints on each slot and between them as well. Well, the second problem is floor planning on multi-die FPGAs. It's also very challenging. The root for this problem is a long net delay due to NAS crossing die boundaries. Previous work shows that this typical medium length routing wire within a single die has roughly 4 times to 8 times shorter delay than the inter-die super long lines, SLLs. To mitigate the long delay, existing solutions differ in their objectives, algorithms, and granularity. The fine-grained method maps the primitives or cells to the tile site level, which is very time-consuming, while the state-of-the-art coarse-grained methods for HLS designs use integer linear programming, which is also kind of slow because you call a solver, especially when if it's called repetitively when you try to work with the directive search. Moreover, they are dedicated to data flow designs, so they cannot handle those designs if there are non-data flow modules mixed. So here we use a toy example to explain the opportunities in this co-optimization flow. In this example, we try to do one step of floor planning followed by one step of directive search to explain why the previous simple concatenation of existing solutions could be suboptimal. Okay. So here we suppose that we have a toy multi-die FPGA with 2 slots. Okay, here having a constraint of 70% resource on each slot. Meanwhile, we have a design consisting of 2 data flow regions and 1 data flow non-data flow module. A and B are submodules in the same, connected by FIFO in the same data flow region, and D and E as well. They are connected by FIFO with different widths, 16 and 8 for between D and E. Well, C is a non-data flow module connected through RAM to the data flow kernels. In this case, for latency optimization, we suppose that each module has a directive to apply because I want to explain it clearly. So we just use one directive, which means that you either apply it or not. Suppose that when you apply it, you'll help the function to use more resource and achieve a lower latency. But for timing optimization, we require that only the FIFO connections are allowed to cross the slot boundaries, this boundary, because we can insert pipelining logic easily into the FIFO channel, while for the RAM interface, RAM connected functions, it's difficult to pipeline. So you need to group them on the single die. That's the constraint. So now we compare, now we try to floor plan and then do the directive search. We compare the result of using 3 different floor planning techniques. The first minimizes the width of the FIFO connection crossing slots. Okay, crossing slots here. So the solution here is obvious, it's 8, right? The min cut solution is 8 between D and E. So A to D are grouped on the same slot here and E on the other one. So then we do the directive search, which means you expand the functions. You try to use trade resource for lower latency. We can optimize the latency by applying directives for B and E because there's not enough space for you to expand all of them. So this is already the best solution in this case. And you can optimize the total latency from 18 to 16 in this toy example. Well, the second floor plan refers to the heuristic of resource balancing between the 2 slots. Module B, C, and D have similar size to the sum of A and E. So you'll see this floor plan. And we can apply directive for B, D, and E. And the total latency is improved to 14 in this case. Well, to compare, an ideal floor plan would be partitioning between A and B, actually. In this case, there will be enough space for the latency bottleneck A to expand itself, and we can reach the minimum latency to improve from 18 to 13 in this case. So from this example, you can see that a previous floor planning method could fail to assist the directive search on multi-die FPGA scenario. And besides, in this case, you see that it's meaningful to have the knowledge of latency bottleneck when you do this code search. Okay, to briefly summarize the research gap and opportunities, now we need a highly efficient co-optimization flow considering multiple objectives. And we need a fast floor planning algorithm that can assist directive search very efficiently to handle the large and non-monotonic design space, and moreover, to support the large design mixing data flow and non-data flow cases. Well, before designing a fast algorithm, we would like to see the original formulation. Right? So floor planning puts the HLS functions into slots on a multi-die FPGA or die on the FPGA. So this naturally leads us to the classic knapsack problem, where you pack items into a bag. We might maximize the value considering the bag's volume and the item's weight, right? So, however, for each HLS function, we have multiple directives and parameters to choose from, which means the item's weight and the value could change during the packing. This leads us to the multi-choice knapsack, where you have multiple classes of items, and we'll try to pick one item from each class to pack it. And we're getting close, but not enough. Since we have multiple types of resources on an FPGA, like flip-flop, LUT, DSP, and BRAM, URAM, all kinds of on-chip resources, it's just like a multi-dimensional knapsack problem. Like in this case, I'm showing you an example of 2-dimensional. You have a weight and height to try to fit into this backpack. Okay, or moreover, in knapsack problem, we consider only one bag originally. When it's full, you stop the packing. But in floor planning, you need to make sure, you have no choice but to make sure that every function is assigned to some slot. So this leads us to the bin packing problem. Well, beside the multi-choice, multi-dimensional bin packing, remember that in motivation example, because floor plan requires that only FIFO channels can cross the die boundaries, and the BRAM connected functions should be grouped on the same die. We have the fourth constraint here. And finally, the number of super long lines crossing dies is limited compared with the intra-die routing resource. It's very limited. So now we have the whole formulation of the problem. Based on it, we develop a very efficient iterative solution. Here I introduce the three main parts in this flow: directive optimization, incremental floor planning, and the pipelining. Well, the top level algorithm is described here. In every iteration, we identify the function with the longest and the second longest latency among the whole HLS design, the bottleneck. In next step, we try to find a special design point, DP, represented by DP, for the current longest function. Okay, this is a new design point, has two special properties. First, it is smaller than the second longest latency in the current iteration, which means that we expect the current bottleneck to be optimized and not the bottleneck anymore in the next iteration. You'll do this iteratively. And second, the DP's latency would be as large as possible, as long as it's smaller than this one, because you do not want to make dramatic optimizations on the latency. It usually come along with a dramatic increase in the resource. So the aggressive changes could hinder the potential improvement in the future. So this main algorithm keeps shortening the latency bottleneck, but the greedy algorithm could easily get stuck in local optima. To handle the non-monotonic design space, we propose a sampling strategy in two directions, looking ahead and looking back. Well, when floor planning for the current design point DP fails, we look ahead for more design points with lower latency. And if look ahead still does not work, then we try to look back. Well, for choosing the how you decide the sampling range for the look ahead, you'll need to see the pipeline and on-roll directive and their parameters, because they are two of the most efficient directives in HLS. Well, this example shows that shows the different sampling ranges effect. This is a snapshot of the directive search for the current bottleneck function represented by I1, J1. It has a latency of 0.8 normalized and 0.1 resource at this point. We start from this original point, black point, and first we go down to check the DP. It has a top priority. Well, since we only have 0.35 resource left on this slot or die, but DP consumes 0.5 resource, it fails in the floor planning. That's when you need to do the look ahead and look back. So now let's say we choose this look ahead step number n to be 1, which means that you'll look for one more design point. This consumes 0.6, so it still fails. And then you try to look back. And finally, you'll stop here. 0.6 latency and 0.3 resource utilization. Well, if you want to spend some more time on the look ahead, then you'll probably reach a better design point like this one, 0.15 latency, yet smaller resource utilization. It could happen because of the non-monotonic design space. Well, in the floor planning, to avoid congestion from a high abstraction, the online packing stage, we have online packing and offline packing, right? The online packing stage applies the worst fit heuristic from bin packing family. Tends to balance the utilization ratio among different resources and different slots. We first check whether a function can still fit into its current slot after applying new directives. If no, we'll sort other slots according to the non-decreasing order of the critical resource and try to pack into them one by one. This is the online stage. And since the online packing tends to spread function evenly on each slot, which is the worst fit heuristic, when there is a dramatic change of resource, say if we have an oversized function, the balance could be harmful because the available resources are also evenly spread on multiple slots, but each time you can only choose one slot to pack your function, right? So here we introduce the offline repacking stage with the best fit decreasing heuristic, which adversarially it compact the floor plan from time to time to make space for the potential large modules. This example shows the floor planning of 5 functions, these rectangles, onto 4 slots. During one step of directive search, the resource of this blue colored function increased from 0.3 to 0.6. And since the other gray functions were already fixed during the previous online floor planning stage, so you cannot move them. And you'll see that you'll find no solution in floor planning for this function, right? No die, it fits into no die here. And to compare, the repacking stage sorts these slots by their utilization in non-increasing order and executes 6 trials in order to move functions from the underutilized slots to those with higher utilization to get compact. So after the offline repacking, the expanded function can find an empty slot during a new round of online packing in this case. That's why offline repacking is stronger than offline repacking and will help the future iteration. When moving the function across slots, as the figure shows, each time a path crosses the boundary between the 2 slots, additional pipeline registers should be added beside the boundaries to break down the long wires. In this example, when the function D is moved to slot 0 to slot 3, you'll see that 2 groups of additional pipeline registers are added in between, separately on both sides of each boundary crossed. This is done incrementally compared with the previous work of some global update. Well, for experiments, we generate large-scale designs mixing data flow and non-data flow kernels. The data flow designs come from PolySA and AutoSA framework, and the non-data flow designs come from PolyBench. As for resource limit, we use an empirical value of 65%, which follows the similar value compared with previous work. We compare FADO with different top-level DSE flow and the floor planning algorithms. The first row, original, means the quality of result for HLS designs with no directive applied. And the second row means that we only use an one-off initial floor planning, followed by the iterative directive search. Under a fixed initial floor plan, you can see that the latency optimization is seriously limited. This underscores why an iterative co-search of the floor plan and directive is very important. The third row means that iterative search using auto-bridge floor planner, the min-cut floor planner, it results in orders of magnitude longer DSE runtime than FADO, the last line, due to repetitively calling the MILP solver. Since it's using iterative bipartitioning, so the ILP solution is not optimal in the end and inferior to FADO in most cases, actually. The last row is FADO's performance using our incremental floor planner. Without loss in the timing quality, we outperform previous solutions in both the overall workload execution time and the DSE runtime. Well, to show the convergence of our framework, we here present the DSE result with different optimization stages. These 4 stages are running sequentially in each iteration, and each one includes the effort of previous stages. For example, the second row offline means the joint effort of this online stage and offline. So in the figure below, in the figure below, we can tell that the blue curve, this blue curve represents the auto-bridge floor planners convergence, and it stopped earlier than the purple and the yellow arrows, which is FADO's convergence path. Well, to conclude, our work produces FADO, an open source framework that co-optimizes the directive and floor plan for HLS designs implemented on multi-die FPGAs. On the one hand, our well-customized incremental floor planning supports both data flow and mixed non-data flow, and achieves orders of magnitude speed up over the global MILP floor planning. On the other hand, our co-optimization enables full utilization of resources on multiple dice and greatly benefits both latency and timing. If you're interested in our work, please check our open source repo. And thank you for your kind attention. Now I'd be happy to take any questions. Thank you.
Thank you very much for your presentation.
Hi.
Could you please address why the FADO can have higher frequency compared with auto SA, or what's the main difference between improvement of FADO?
Actually, it's without loss without loss of the timing quality. In most cases, I think because the ILP sometimes the ILP, the target of ILP is min cut in this case. It's not directly working on the critical path. So there's some uncertainty. And in these 6 synthetic benchmark, our observation is that FADO's adversarial floor planner using the online and offline stages can result in good frequency, but when you change, I cannot say for sure. To be honest, I cannot say for sure that it will always have a good case like this.
Thank you. So it's it depends, right?
Sorry.
So it depends on applications, not always the case.
Yeah, I'm being honest here because here poly-SA and auto-SA generated benchmarks are the systolic array types, and it has its own feature, the topology. Well, I'm trying to make it as general as possible, so I use the poly bench, which is also used for CPU and GPU, right? It's general benchmarks. So we need to do more tests if you want to really prove it's working so robustly.
Yeah. Thank you very much.
Thank you.
One short question.
I have a question. So when you estimate the latency and resource utilization, do you use the HLS report? And if so, the HLS report will not tell you the latency for kernels that do not have compile time, like you don't know the iterations at compile time. So is it only limited to kernels that you know the behavior at compile time? If you have kernels that you cannot estimate the latency with the HLS report, can FADO still handle these cases?
Yeah, I understand your concern because you can add some pragmas, like if you have a loop with a variable type loop bound, then the HLS probably will fail to give you an estimation of the latency, right? So there are pragmas like loop trip count or something to tell the tool about it at the compilation time. So yeah, in our cases, we use a pragma to give it the information.
But if the latency is variable, how would you search for the best overall latency?
It will happen for loop trip count. You can the pragma, you can set the main and the max value to indicate the trip count, so it will give you a range of the latency during compilation. Yeah,
I see. All right, thanks.
For more details, you can feel free to ping me offline. Yeah.
Well, thank you very much for that.
Thank you.